Today we're going to look at applications of linear equations in one variable. In the real world, math equations aren't written out the way we find them in textbooks and problem sets. Math is still used, but you have to use critical thinking to find the solution to a problem. We can use Polya's problem-solving techniques found in How to Solve It 1945 to help us form a strategy to solve these real-world problems. Polya's problem-solving techniques is composed of 4 parts. The first part is to understand the problem, then devise a plan, carry out that plan, and then look back. To understand the problem, we want to read through the problem completely. What is it asking? What do you know? What do you need to know? How are these things connected? Then devise a plan. Write things down. Draw a picture. What kind of answer should you get? Can you estimate what the answer might be? To carry out the plan, we use a strategy to solve the problem. We want to be organized and write things down. We will work through each step until you arrive at a solution. As we look back, we want to consider if our answer is reasonable, does the answer make sense, could there be more than one right answer? Let's take what we just learned and solve some problems. A company will install 500 square feet of sod for $625. Additional square footage can be purchased for $1.50 per square foot. How many square feet can be purchased for $820? As we read through the problem, we can see that the 500 square feet has an associated cost of $625. Then each additional square foot, which we don't know how many more we will need, so let's call this X, can be purchased for $1.50 per square foot. And then we can see we have this budget or this spent amount of $820. That was our total cost. So we want to know when is $625 plus 1.50 times X equal to 820. This will start telling us how many additional square feet we bought. To solve, we want to isolate the X, so we'll start by subtracting 625. This says 1.5x is equal to 195. We'll divide by 1.50, which tells us X is equal to 130. What's very important is that we always look back at the question. And the question said, how many square feet can we purchase for $820? The answer is not 130. 130 is the additional square feet we will get on top of the 500 that came for the 625. So our answer will be 130 plus 500, which is 630 square feet. So we always want to make sure we're looking back to say, what kind of answer did we get? Does it fit what we were doing? And did we correctly answer the prompt? A conference rental space charges $75 per hour plus $25 for Wi-Fi service. Find the number of hours that corresponds to a $700 rental bill. So again, we're talking about money. So we have $75. This is per hour. So let's let our hours be X again. $25 is a flat fee, so we don't have to do that more than once. So let's just write flat fee. And then our total bill is $700. So what we want to do is look at 75 times X plus the 25 and say that's equal to 700. Like the last problem, we want to start by isolating X. So I'm going to move the 25, subtracting it from both sides, so 75X is equal to 675. Then we're going to divide by 75, which says X is equal to 9. This time, that is our answer, that 9 hours, or the number of hours we rented the space for if we spent $700. Our last problem has 3 parts. Let's start by reading the problem. The water elevation at a large dam is 1,215 feet and is decreasing by an average of 13 feet per year. Give a linear equation for the water elevation W in terms of T, the number of years from now. So water elevation is our height, and it's going to be 1215 minus 13t. So we're looking at where do we start? So we started at 1215, and because it's going down, we're subtracting to show that decrease by 13 per year. We do 13 times t. Then it says find the elevation of the water in 6 years. So let's write W is equal to 1215, and then we're going to do minus 13 times 6. This says I have 1215 minus 13 times 6 is 96, which says our water elevation will be 1,119 feet in 6 years. Part C says if the dam will not function once it goes below 1,007 feet, find the number of years that the dam will be functional if it continues to decrease by 13 feet per year. So we're going to take the equation we had before, W equals 1215 minus 13t, and we're going to set W to be 1,007. We'll leave our 1215 minus 13t and solve for t. I'll start by subtracting 1215 from both sides. This says negative 208 on the left is equal to negative 13t on the right. I'll divide both sides by negative 13, which says t is equal to 16. So if we continue to have this same reduction of height in the dam, we only have 16 more years of service for the dam.